Hey everyone, welcome to today's Explainer. If you're an engineering or tech student, you already know that having a brilliant idea is only half the battle, right? Today we're diving into the exact framework that takes those abstract theories and turns them into concrete, working reality. Because engineering design isn't just about throwing numbers at a whiteboard and hoping something sticks. It's a systematic, highly rigorous process of problem solving. Let's dive right in. Now, you might be wondering, why is a strict process so absolutely crucial? Well, let's look at what happens when it breaks down. Back in 1999, NASA lost the Mars Climate Orbiter. And get this, the root cause wasn't some incredibly complex astrophysics failure. No, it was a catastrophic breakdown in step one of the engineering process, problem definition and communication. Literally, one team at Lockheed Martin used imperial units, pound seconds, and the NASA team used metric, Newton seconds. That single, totally preventable disconnect cost $125 million and completely doomed the mission. It just proves that even the most brilliant engineering falls flat on its face without a rigorous process. So to make sure we don't make any $125 million mistakes, here's our blueprint for this explainer. We just covered the cost of bad process, and next up we'll hit engineers in modern society, the 9-step iterative engine, defining the problem, a quick knowledge check, and finally, bringing ideas to life. Section 1, Engineers in Modern Society. Look, modern engineering operates inside a massively complex societal web. It's really not just about crunching math and physics anymore. You actually have to analyze the social and environmental impacts of whatever you're building. We're talking about navigating ESG, that's environmental, social, and governance frameworks, so you're constantly balancing profits with people and the planet. Plus, integrating sustainable development, professional ethics, and occupational safety and health standards, those are just as critical as your structural calculations. That is how we prevent disasters and create actual lasting value in the real world. Moving right along to Section 2, the 9-step iterative engine. I want you to picture this mechanism like a massive 3D animated engine where every single gear has to mesh perfectly. We call this the IDEA framework: identify, develop, execute, and assess. It's a 9-step iterative engine. And I say iterative because, as you know, engineering isn't a straight line. You loop back, you refine, and you continuously improve. If one gear slips, the whole thing grinds to a halt. Our engine always kicks off with 3 foundational steps. First up, identifying the problem. Second, gathering the needed information. And third, searching for creative solutions. This right here is your crucial groundwork. Notice anything? Yeah, we haven't built a single physical prototype yet. If you rush past these steps because you're eager to start building, you're practically asking for a Mars orbiter level disaster. Which brings us to Section 3, defining the problem. Let's do a quick comparison. I like to call this the void versus the blueprint. Listen to this terrible, vague problem statement. Design a short, inexpensive device to control energy of a fast car. Deceleration shouldn't harm the driver. I mean, what does fast actually mean? What is inexpensive? It's entirely subjective. Now compare that to a real engineering blueprint. Design an energy absorption system for a 2,500-pound car traveling 60 miles per hour. Max length, 10 feet. Max cost, $10,000 per unit. Max deceleration, 6 Gs. See the difference? A true blueprint leaves absolutely zero room for misinterpretation because it's built entirely on objective numbers. To get to that level of crystal clear precision, engineers lean on the SMART framework. It's basically the gold standard for defining a problem. Your problem has to be specific, measurable, achievable, relevant, and time-based. If your problem statement doesn't check off every single one of those 5 boxes, well, you're just not ready to design yet. Go back to the drawing board. Okay, so once your problem is locked in, you jump into ideation, searching for those brilliant solutions. But let's be real, what happens when you hit a wall? You've got to rely on cognitive obstacle removal techniques. You can do some brainstorming, where you just rapid-fire generate ideas without any judgment whatsoever. You might use attribute listing, where you isolate specific variables. Or you can try forced relationships and incubation, basically just stepping back and letting your subconscious mind connect the dots. All right, Section 4, knowledge check. Let's see if you've been paying attention. Time for a rapid-fire interactive quiz on the identify and ideate phases. Play along and answer out loud. Here's question number 1. What do the 5 letters in the SMART framework stand for when defining an engineering problem? Think back to that blueprint we just looked at. And the answer is specific, measurable, achievable, relevant, and time-based. Those are the 5 massive pillars of problem definition. If you got all 5, awesome job, you're totally on track. Let's throw question 2 your way. During the initial idea generation phase of brainstorming, what critical rule absolutely must be followed regarding the evaluation of ideas? No judgment. Seriously, you have to completely suspend judgment to let those truly out-of-the-box creative solutions bubble up to the surface. Evaluation comes later. Brainstorming is strictly about generation. Okay, let's go a little deeper for question 3. Which creative solution technique involves isolating the major characteristics of a product and listing ideas on how each characteristic could be changed? That would be attribute listing. By isolating individual variables like the material, the shape, or the power source, and then listing alternatives for each one, you systematically spark new innovation. Fantastic job if you nailed those.
Section 5. Bringing ideas to life.
So, we are now entering the execute and assess phases of our iterative engine, where those abstract ideas finally become real. Once you've evaluated and picked your best solution, you hit step 7. As our source material beautifully puts it, plans and specifications are the engineer's means of describing sufficient detail about a design so that it can be produced or constructed. Guys, this is your critical translation layer. You're taking this brilliant concept from your brain and communicating it flawlessly to a manufacturing team or a contractor. And once again, this is exactly where precision matters most. Finally, we wrap up the process with steps 8 and 9. Implementing the design isn't just tossing the plans over a wall and hoping for the best. Engineers have to actively oversee the construction or production. And then comes step 9, monitor and redesign. Remember our 3D animated engine from earlier? It's iterative. Once your design is built, you assess how it performs out there in the wild, you gather new data, and the whole cycle of innovation starts all over again. We have covered a ton of ground in this explainer today, from the heavy societal responsibilities of a modern engineer right down to the nuts and bolts of the 9-step idea framework. But if you take away just one thing today, let it be this. Theoretical knowledge is utterly useless without a rigorous process to guide it. So, to all of you future tech leaders and engineers watching, I challenge you to take this framework, apply it meticulously to your own work, and ask yourself, what will your blueprint build? Thanks so much for joining me today, and keep designing.